Today's lecture, we're going to be talking about stoichiometry, which is a process of playing with chemical equations to balance them. So the first question we need to ask is, what is a balanced chemical equation? And the next question is, how do we balance an equation that's not balanced? So first, we'll do some review of what chemical equations are. We have been working with them throughout the semester, so hopefully you're familiar with them, but we're just going to go over some of the parts. So a chemical equation basically represents a chemical reaction. So that's a chemical reaction is a process in which a chemical change takes place. So for example, in the chemical equation shown, we have silver nitrate plus copper that reacts. The arrow indicates that reaction occurs, and then we end up with copper nitrate and solid silver, and we also release some energy in this process. So in this equation, the silver nitrate and copper are reactants. That's what we start out with. And the copper nitrate and solid silver and energy are products. Now, sometimes we indicate energy in a chemical equation, and it can be a reactant or a product, depending on whether the reaction is endothermic or exothermic. So this is an exothermic reaction, which is one that releases energy, so it's a product. But we don't always indicate energy. It depends on what you care more about. If you're trying to extract energy, say, from a fuel, you're going to be very concerned with how much energy is released. If you just want to make solid silver, then you're not going to care so much. Although you at least need to know whether you're going to have to input energy into the reaction to make it occur. So another thing that we sometimes, but not always, show in chemical equations are symbols that indicate the state of each substance. So S, it's always each symbol is put in parentheses right after the atomic symbol, and S means solid, L means liquid, G means gas, and AQ means aqueous. Now, aqueous is a solution, a water solution. So, for example, if you take table salt or sodium chloride and put it in water and mix it up so it's all dissolved, that is an aqueous solution. You can also make an aqueous sugar solution, so anything that dissolves in water. And we have this as its own state. It's not really a state like solid, liquid, or gas, but it is an important consideration when we're talking about chemical reactions, because, like, particularly in biology and in the chemistry lab, many reactions do occur in aqueous solution. So, like, think about your cells. Everything is basically dissolved in water in the cells, and all the reactions that are happening there are occurring in aqueous solution. So that's why we list this as one of the states. Now, you might also remember from the beginning of the semester the first law of thermodynamics, which states that matter and energy cannot be destroyed. They can be converted to different forms, but you always end up with the same amount that you started with. Now, in terms of matter alone, when we're just dealing with matter, this law can be broken down to state that matter cannot be created or destroyed, but it can be rearranged. So this means that in a chemical reaction, you can rearrange how atoms are bonded with each other. However, you must always end up with the same number of each atom that you started with. So let's take a look at a classic chemical reaction, or a common one. So this is a combustion reaction with methane. So CH4 is methane, which is the primary ingredient in natural gas. And combustion is reaction with oxygen. So we have methane plus oxygen, and this when it combusts, it produces carbon dioxide and water. So basically, in this reaction, the subscripts show the number of each atom in the molecule. So CH4, or methane, has one carbon, so we don't show the one, and it has 4 methanes. But not only do we have subscripts, so there's also subscripts for the oxygen diatomic molecule, For carbon dioxide, there's 2 oxygens and there's 2 hydrogens in water. So those are other scripts. But in addition to these subscripts, we also have coefficients. Now, the coefficients show the number of each molecule in the reaction. And the coefficients must be basically written in a way that indicates a proper ratio of products and reactants so that we end up with the same number of each type of each atom on both sides of the equation. So carbon, for example, there's only one in the methane in the reactants, and if we look at the products, there's also only one. So we can write down that there's one in the reactants and one in the products. Now let's go to hydrogen. There's 4 in the reactants, all in CH4. And then if we look at water, there's 2 in each water molecule, but 2 water molecules are formed. So that means there's 4 waters or hydrogens in the reactants and 4 in the products. So that is balanced as well. And then, and again, when we look at oxygen, we see that each O2 molecule has 2 oxygens, but there's 2 of them, so that's 4 altogether. And if we look at the products, we can see that oxygen is actually in 2 different molecules. There's 2 in carbon dioxide, and there's 1 in water, but there's 2 waters, so that's 2. So that 2 plus 2 is 4, so that means we have 4 oxygen atoms in the reactants and 4 in the products. So when the products equal the reactants, we say that the equation is balanced. So let's consider that we took the same equation and did not balance it. So in other words, we showed all of these same compounds and molecules, but we did not show the coefficients. It would not be balanced. In other words, the number and kind of atoms in the products would not be equal to the number and kind of atoms in the reactants. So basically, just to summarize, coefficients represent the number of molecules, or they can also represent the number of moles of molecules. So that's basically if you have 1 mole of each thing, that's the same ratio as if you had just 1 of that thing. So it can represent the number of molecules or the number of moles. Either way, the ratio is always the same. So in other words, if we react methane with oxygen, we're always going to end up with a ratio of 1 carbon dioxide formed for each methane combusted and 2 water molecules formed for each methane combusted. And also we can look at the ratio within the reactants and products. So you're going to need 2 oxygen molecules to completely react to the methane. So how do we balance chemical equations? Looking at this equation, we have one element, rubidium, that is a pure element, and it's not a molecule. Bromine is a pure element as well, but it is a molecule. And then on the right, we have a compound, a ionic compound. So on the left, since we have 2 different items, what I usually like to do is look at the ones that are molecules or compounds first and save the pure non-molecular elements for last, and that's because these are a little bit harder to deal with, and then it's easy to use to figure out what the ratio of the pure element is. So in this case, I'm going to start with bromine. We have 2 of them on the left, and then over on the right, in this unbalanced equation, you can see that we only have 1 bromine. So basically, oh yeah, and I just want to point out that in balancing this equation, we can't change the subscripts because this is actually what is the products and reactants of this reaction. So the only way that we can change it is by changing the coefficients. So we're going to do that now. Again, we have bromine Br2 on the left. That means there's 2 of them, and we only have 1 bromine on the right. So we're just going to write down 2 on the right-hand side of the equation. So now we got to look at our other elements. So rubidium bromide, there's now 2 of them. So that means that we're going to have 2 rubidiums. So at this point, it looks like the equation is balanced. And right here, I could write that I have one bromine, but the one, you don't have to write it. It could be useful when you're balancing these, just to clarify to yourself that you did take into account that atom or molecule. But if you look in a book, there will not be a one, it'll be just left blank. Now that we're done with this, we're going to check our work. And if we look at rubidium, there's 2 in the reactants in solid rubidium, and there's 2 in the products in rubidium bromide. And if we look at bromine, again, there's 2 in the reactants and 1 Br2 molecule, and there's 2 again in the products in rubidium bromide. So this is a balanced chemical equation. And that's essentially what stoichiometry means. It's a ratio of atoms and molecules in a balanced chemical equation. So we can say that the stoichiometry of this equation is 2 rubidiums plus 1 bromine molecule react to form 2 rubidium bromide. Okay, we're now going to do a little bit more complicated example. So this is a reaction of iron with oxygen to form iron oxide. And this is the reaction that produces rust, and iron oxide is the reddish color substance that you see on rusty objects. So to look at this equation, at first it doesn't look too hard, but if you look at the oxygen, there's O2 on the left, and then there's FtO3, so it's a 2 to 3 ratio. So remember, we can't fiddle with these subscripts because these are the actual reactants and products. This is actually what happens. So what we do have to do is fiddle with the coefficients that go before each of these chemical substances. So to do this, again, I would leave iron off and start with the oxygen. Now we see that it's a 2 to 3 ratio. So how do we balance this? Well, it turns out that what we need to do is basically multiply out in a ratio so that we'll have an equal number of oxygens on each side. So to do this, we can multiply 3 times 2 in the reactants and 2 times 3 in the products. So 2 times 3 equals 6 and 3 times 2 equals 6. So that means that we have the oxygens balanced. Now when we do this, we next look at the iron on the right side of the equation. So there's 2 Fe2 and Fe2O3, and then there's 2 of them, so that's 4 total. So we need 4 irons. So again, I didn't write the little table here, but you may want to do it or just kind of do a visual check. So we've got 4 irons on the left, and then 2 times 2 is 4 irons on the right, and 3 times 2 is 6 oxygens on the left, and 2 times 3 is 6 oxygens on the right. So this is a balanced equation.